A proton moves along the positive x-axis with a velocity of 1.0 times 10 to the 7th meters per second. As it passes the origin, what is the magnetic field at the following points? The first point is at the x-coordinate of 1.00 millimeters along the x-axis. The second point is at the y-coordinate of 1.00 millimeters along the y-axis. And the third point is a point in the xy plane with an x-coordinate of 1.00 millimeters and a y-coordinate of 1.00 millimeters. Let's start with a sketch of the scenario. We will have the x-axis be represented as the horizontal axis, the y-axis will be a vertical axis, and the z-axis will be an axis coming right out of the page. Let's position our positive particle at the origin of this coordinate system. The velocity at which this positive particle is moving is along the positive x-axis, given as the vector v, where the velocity vector is equal to 1.0 times 10 to the 7th meters per second. For part A, we're looking for a point on the x-axis at which we want to evaluate the magnetic field. I will label this point A with coordinates A, 0, 0, where I'm defining lowercase a to be equal to 1.00 millimeters. So in order to determine the magnetic field at point A, we are going to apply the Biot-Savart Law. Now remember, the Biot-Savart Law tells us that the magnetic field at a point is equal to mu naught, the permeability of free space, over 4 pi, times the source charge's value, times the cross product between the velocity vector and the unit vector indicating the relative position of the point and the source charge, over the distance to that point squared. So let's label some of these vectors. We have the velocity vector in our picture. This will represent the relative position vector between point A and our charge. And this is given with a magnitude of r sub A. So for the Biot-Savart law, the magnetic field at point A is based off of the distance to that point, where we are defining r sub A to be equal to A. That's just the distance. Now, because r hat A is a unit vector of magnitude 1, we could easily rewrite the Biot-Savart law in terms of the magnitude of the cross product between the velocity and that relative unit vector. And that's just given as QV sine of the angle, in which I'll call this reference angle theta A, over r squared. Well, we have to determine what theta A is, because we know the magnitude of the velocity, we know the magnitude of the position, or rather the distance between point A and the source charge. So we need to determine the angle theta A. When we look at this, we see that the velocity vector is parallel to the x-axis, and the relative position vector is also parallel to the x-axis. Since these two vectors are parallel, the angle between them is 0. And remember, the sine of an angle that is 0 is equal to 0. So this means that the magnetic field at a point on the x-axis with this source charge moving along the x-axis is equal to 0. Now, this makes a lot of sense, and it underscores an important conceptual point. The magnetic field for any point along the line of motion of a moving charge is equal to 0. So we calculated this magnetic field at a point A on the positive x-axis. Well, even if we take a point on the negative x-axis, the magnetic field at that point will be equal to 0. Like, for example, you could see that pretty easily by looking at the relative position vector for that point on the negative x-axis. And if we look at the angle between that relative position vector, which I'll just call this relative position vector r sub a prime, and we look at its orientation relative to the velocity vector, we see that the angle between those two is 180 degrees. And if we were to apply this with the Biot-Savart law, being mu naught over 4 pi qv sine of 180 degrees over r squared, we would get that the magnetic field is 0 because the sine of 180 degrees is 0. So what this reveals to us is that any point along the line of motion of a moving charge, the magnetic field due to that moving charge is equal to exactly 0. There is no magnetic field along the line of motion due to that charge.